Everyone, my name is Canver. I am so glad to be here for giving presentation regarding my major assignment. Thank you in advance for your patience. Welcome to the presentation on the comprehensive reconstruction and sealing of a crucial 5.92 kilometer section of Kalamina Road, stretching from Benjini Drive North to the car park and Kalamina George within our national park. Project goal is to establish a 6-meter wide sealed road with 0.5-meter wide unsealed shoulders on each side, creating a total formation width of 7 meters. This presentation will delve into the project's water management strategies, the usability of gravel supplies, environmental considerations, and detailed construction planning to ensure both infrastructural integrity and environmental preservation. In this phase of the investigation concerning the proposed road corridor, addressing water management considerations has become essential. The climatic conditions of the Carigini region, characterized by a combination of tropical and semi-arid climates, present unique challenges. According to the information obtained from Wikipedia, summer days in this region often see temperatures soaring above 40 degrees Celsius, while winter nights can bring frost. These extreme weather conditions necessitate effective water management strategies to ensure the durability and safety of the road infrastructure. Highlighting the importance of efficient drainage systems, water retention methods, and the use of materials and designs suitable for such a harsh climate. The median rainfall data collected from Auski-Mongina Roadhouse, Hammersley, and Hooley stations, as shown in tables, highlights the need for careful planning of the road construction phases. Given the project's restricted 6-week construction schedule mandated by the Department of Biodiversity, Conservation and Attractions, organizing the construction during optimal weather conditions is crucial. Heavy rainfall, particularly common in January, February, and March, often halts highway construction due to the saturated soil conditions that impede quality control measures such as surveying and in-situ tests. Proper compaction is critical, with the guideline advising placement of granular materials slightly dry of optimum moisture to avoid overcompaction. Considering the rainfall patterns, November and the first half of December post-tourist season are identified as the ideal months for construction. The practice of water management in transport corridors focuses on 3 key elements: groundwater movements under the corridor, transverse water flows across the corridor, and water movements along the corridor. These elements should be managed together, though this is not always done. For roads, railway, and airports, groundwater is the most critical factor as it affects soil stability and foundation integrity. Transverse drainage is crucial in rural areas, while managing longitudinal water flows such as stormwater removal is more important in urban areas. The relative importance of these elements can vary depending on the transport mode and location. At the scope of projects, it's discussed our approach to moisture control systems during the construction and service stages of our projects. We have determined the catchments by analyzing the topography of the project area. As part of the project scope, we need to implement 7 culverts. These culverts are critical for challenging water under roads and must be strong enough to support both construction and highway traffic loads, along with the loads from the road formatting itself. Throughout the road construction and subsequent service period, it is essential to use appropriate drainage structures to prevent erosion and pavement damage. To this end, we are employing table drains and middle drains to effectively manage surface water and groundwater, keeping them away the corridor. Also, it has been required to design floodway for supporting the hydraulic capacity due to the large quantity of water collecting via long stream. Another key aspect of our project involves managing water flow from catchment 3, which discharge into existing natural stream running parallel to our road corridor and close to the elevation. Excessive rainfall in this section could significantly impact the road corridor during both the construction phase and future use. To mitigate this risk, we have designed table drains along the corridor that will tie into the proposed culverts, ensuring efficient discharge into the crossing stream. Within the scope of our project, we have identified several locations where these drainage structures, table drains, middle drains, and culverts need to work in tandem to manage water flow during construction and subsequent service periods. These critical sections are generally located at the lower points of the corridor. As determined by the topography, we are designing culverts to facilitate water crossing and are also incorporating proposed drains to collect water flow from the related catchment. This water will then be discharged through the culverts into the natural stream bed, ensuring effective water management throughout the project's lifespan. As discussed in previously, one particular area of focus is culvert 4. This culvert needs to handle the flow rate from catchment 2, the largest catchment in our project, covering an area of 75 hectares with a 3% water flow grade. Given the region's tropical climate, which experiences heavy rainfall during the wet season, we face significant challenges. Using a bridge to address these hydraulic demands would be very costly, requiring the lifting of vertical alignment, leading to high construction expenses. Therefore, we have determined that a floodway design is the most ideal solution for this section of the road. Balancing effectiveness and cost efficiency, floodway design is the most ideal option for this section of road. For the floodway design, site distance, signing for traffic safety, proper pavement structure, and road geometry are paramount. It has been required to calculate the water velocity for interrupting about floodway upper structure. As a result of this, it has been determined to use Type 3 floodway typical cross-section of Main Roads, Western Australia. Water intended for drinking and camping must meet potable water standards to ensure safety. Discharge should be directed to non-erodible surfaces and monitored to prevent contamination and erosion. It's crucial to ensure that water discharges do not generate runoff, affect flora and fauna, or cause flooding, and that all water remains within site boundaries. These procedures are in place to ensure environmental compliance and safety through all construction and site activities. In our project, we have identified a significant issue with total suspended solids in water obtained from borehole next to gravel pit B. The TSS level is extremely high at 950 mg per liter, indicating very turbid water. To address this, it has been determined to use flocculants to reduce TSS and turbidity before using the water on site to prevent environmental pollution, particularly near sensitive areas like national parks and campsites. According to the New South Wales government's 2019 Water Discharge and Reuse Guideline, all water used at construction sites must be thoroughly tested and treated to meet specific quality criteria. Before any water can be discharged or reused, it must be checked for oil and grease. pH levels and TSS salinity should also be assessed. If necessary, based on site-specific conditions, these tests must be verified by the environmental manager. If the water meets the criteria, it can be reused for purposes such as dust separation, compaction, or landscaping. At the scope of the project, pavement design has been determined with 150 mm sub-base material with minimum CBR 30%, 100 mm base material with CBR 80%. Also, this report has discussed the select fill material applications and design considerations. For the consider the supply of the materials, it has been determined 2 gravel pits around the area of the project, which are Pit A and Pit B. Project involves utilizing gravel reserves from 2 pits for pavement materials, Pit A with 9,000 cubic meter and Pit B with 7,000 cubic meter for constructing the 6-kilometer corridor. We need approximately 4,200 cubic meter of base material and 6,300 cubic meter of sub-base material. Pit A is 7 km from the project start, while Pit B is 22 km away. The road between these pits poses challenge due to its horizontal and vertical geometry, leading to higher vehicle operation costs and potential delays. The Department of Biodiversity Conservation and Attractions has set a strict 6-week timeline for the project. Therefore, we have decided to use materials from these pits for both the current and future road sections. Ensuring compliance with main roads Western Australia specifications, these specifications require careful assessment of material properties including CBR, plasticity index, and particle size distribution. By strategically sourcing materials, we aim to meet project requirements efficiently and within environmental goals. For the comment regarding the usability of gravels obtained from pits, required to compare the target values as per specifications. After careful consideration, we have determined that the material from Pit A is suitable for both the base and sub-base layers of our road construction projects. On the other hand, the material from Pit B doesn't meet the approval standards set by the government. As a result, most of the base and sub-base materials will be sourced from Pit A. This decision is based on 2 key factors: the proximity of Pit A to the project sites, being just 7 km away, and the suitability of its material properties. This approach ensures we use high-quality material and maintain cost efficiency in transportation, meeting all project requirements effectively. This section of our project is part of a larger 37-kilometer road construction effort. Given the material supply restrictions in the region, we have made strategic decisions to ensure adequate material supply for the entire project. It has been determined to stockpile existing road materials, including lateritic cap rock, for use in other sections. For the low traffic and sealed roads, we have adopted the standards from OSROS, which specifies minimum CBR values and layer thickness for U3 class unsealed pavements. At Calamina Road, with a peak traffic of up to 100 vehicles per day, we classified it's a U3 type road. This classification requires a 100 mm rearing course and 150 mm sub-base layer. Considering the total volume of materials from the existing road, which has a 7-meter platform, we have approximately 10,500 cubic meter of material available for other sections. This strategic approach ensures we have sufficient materials to meet the needs of the entire road construction project. As a result of this application, after 250 mm excavating from the existing surface, additional 75 mm rock surface will be excavated as per designer's suggestion to use as a base material for other sections of road projects. Compaction in road construction, especially with granular materials, is vital for increasing soil density by reducing air voids. It must be done at the moisture content between 90% and 110% of the optimum moisture content. With Western Australia, main roads specifying through mixing of gravel, base course and sub-base materials to a moisture range of 85% to 115%. Optimal moisture content followed by 24-hour curing periods. Compaction should start within 72 hours after curing, targeting dry density ratios of 94%, 96% for subbase and 96%, 98% for base material. Compacted in 150 mm and 1 mm layers, respectively, a static smooth drum roller is used initially, followed by multiple passes with a vibratory roller. Weather conditions must be managed to maintain optimal moisture levels. For flatway sections, cement-treated base is compacted immediately after mixing with attention to the edge compaction using shoulder materials. The compacted CTB should be smooth, well-graded, and free of defects with final adjustment made using precise electronic surveying equipments. The road corridor project in the national park necessitates careful environmental considerations to mitigate impacts on flora and fauna. Key concerns include managing high soil salinity and ensuring water quality, with water management being crucial to the region's high salt content. Salinization caused by rising saline water tables poses as a significant threat to soil fertility and vegetation. To address these issues, an environmental management plan must be prepared, detail the limits of the vegetation removal, protecting sensitive areas, and employing sustainable construction practice. Vegetation clearance should be minimized and planned to prevent erosion and weed invasion, with topsoil from native areas reused promptly. Additionally, site investigations involving arborists, ecologists, and park managers will identify and protect vital flora. Project areas identify threatened species such as the western pebble mouse, prompting the integration of a fauna and flora management plan into the environmental management plan. An ecologist and fauna spotter catcher will oversee the clearing stage to rescue and relocate affected species. To minimize environmental impact, the project will use surface miners for vibration-free excavation and maintaining all equipment according to manufacturer specification. Landscaping will coincide with construction to control erosion and establish vegetation, with drainage solutions employing grass seeding, erosion mulch, and turfing. Fauna crossing, including roped ladder crossing and log culverts, will be implemented to mitigate habitat fragmentation, support species movement and interbreeding, and enhance biodiversity by providing safe passages for animals, thereby promoting ecological balance and reducing the risk of species endangerment. Pre-construction and construction planning. The pre-construction process for the Calamina Road project, constrained to a 6-week compression period, involves extensive planning stage, including site investigation, plan development, environmental and ecological assessment, stakeholder engagement, design review, procurement, construction planning, and obtaining necessary approval and permits. Site investigation covers material compliance, ecological surveys, hydraulical studies, and utility surveys, ensuring minimal environmental impact and logistical efficiency. Detailed management plans are developed to maintain quality, safety, traffic, and environmental standards. Environmental assessments focus on protecting threatened species and managing water effectively. Stakeholder engagement ensures alignment with conservation and cultural values. Design adjustments and material specifications integrate site insights to enhance resilience. Procurement involves selecting experienced contractors and sourcing high-quality materials. Construction planning outlines activity sequences, equipment logistics, and water management, finally obtaining regulatory approvals, including environmental impacts, assessments, and various permits ensures legal compliance and environmental protection. Construction activities of Calamina Road involves a series of meticulously planned stages to ensure timely completion within 6 weeks while minimizing environmental impacts. Mobilization begins with transporting equipment and materials to the sites and setting up a construction camp with adequate water and waste management system. Initial site preparation includes clearing the construction area while preserving protected trees and habitats, establishing temporary access roads and implementing drainage controls. Drainage and score protection measures are then constructed, including table and meter drains and protection in high-velocity areas. Gravel is sourced from identified pits, transported to the site, and tested to ensure compliance with CVR specifications. Floodway construction follows, involving assessments and implementation of score protection based on water velocity. Pavement construction includes laying subbase and base materials with proper compaction, applying a seal coat, and constructing adequate shoulders. Finalization and demobilization involve performing finishing works like signage and road markings, cleaning up the site, and removing temporary structures. Post-construction monitoring is conducted to assess road performance and environmental impact, with any necessary maintenance or adjustments made to ensure long-term functionality and compliance with environmental standards. At the scope of the project, Gantt chart has been prepared and showed and illustrated the table. Thank you very much for your listening to me. Kind regards. At the scope of the project, Gantt chart has been prepared and showed and illustrated the table.